You would then have to use the right-hand rule to get the direction. Questions to hear? All right. How does this help us? I have an object here. Think of a meter stick that's pinned in the middle. I apply a force of 10 newtons up here, and I apply a force of 10 newtons right there. Let's just simplify it. Let's just assume this takes place in a gravity-free situation. There is absolutely no distortion of space or time. There is no large planet nearby. This is just, those are the only two forces acting on it. It's a closed system. Is this in equilibrium?
Yeah.
Yes.
And why are you saying, why did both of you say yes?
Because you're exerting the same amount, like there's 10 on both sides basically, and they're in the same, like they're in the same spot on either side.
All right. If this thing starts at rest, will it stay at rest?
I mean, if you come like, I mean, you're asking about it, was it the first Newton law or the second law? Where it says if like an object is in motion, it stays in motion. Somewhere is the first one.
Inertia.
Yeah.
So you said it would not stay at rest?
She was saying the law of inertia.
So you're saying it would
Object
stay
in
at
motion
rest?
stays in motion.
Yes.
An object at rest stays at
Yes.
rest.
So if I took this meter stick and I pushed 10 newtons here and 10 newtons here, it would stay at rest.
No,
That keeps
because you
spinning.
acted,
So,
I thought that's what you were at, like,
Yeah.
when you said at rest.
well,
You're saying
Newton's first law is an object at rest will stay at rest
stays at
unless what
rest,
happens?
And then after you apply the force, it's gonna keep spinning in equilibrium because, speed should be constant.
But while the force is being applied though,
Velocity.
I mean, the argument that Chloe made was that I have 10 newtons up, 10 newtons down, it would be an equilibrium. And I thought equilibrium meant if it's at rest, it would stay at rest. If it's moving, it would stay at that constant velocity.
Well, velocity's constant, not necessarily zero.
Yeah, but if I started at rest, it's zero. All right. Obviously, we need to somehow deal with this because if that's at rest, that's not staying at rest. If you've ever spun anything, you know that if you push on it opposite sides of the pivot point in opposite directions, that thing will spin. There is an equilibrium, so if I just said equilibrium, I would agree with you. Technically, what you have, the equilibrium is, it's in linear equilibrium. Otherwise known as translational equilibrium. Linear and translational can be used interchangeably. Just like rotational and angular can be used interchangeably. So it is in linear equilibrium because for the reason that Chloe said, I have 10 newtons up, 10 newtons down, it would stay. There is part of this though, that because it's in linear equilibrium, there is part of this that actually will stay at rest. What will stay at rest?
The center. The center.
Yes. So in this situation, the center of mass will stay at rest. The axis of rotation will stay at rest. But obviously the object itself won't stay at rest, it'll start to spin. So it is in linear equilibrium, it is not in rotational equilibrium. Or we could also go angular.
So, why did you say that?
I have 10 newtons up, I have 10 newtons down. So
But not as far as like the rotational.
as far as rotation is concerned, let's take a look at not the force, but the torque. That's what I want. I have this R right here. I'll call this R2 and then R1 over here. We'll call this force 1 and force 2. If I look at the total torque acting on this, the total torque would be the sum of the torques, torque 1 plus torque 2. Torque is R cross F. So this is R1 cross F1 plus R2 cross F2. What is the direction of R1 cross F1?
Zero.
Not 0.
What are you asking again?
The direction of R1 cross F1. This piece right here, I've got a cross product, that's an R. I got a cross product, it is a vector product, my answer has to have a direction.
Clockwise.
Okay, let's be more sophisticated. Okay, let's be more sophisticated here. Let's set up I hat, J hat, and K hat.
Is it negative?
Negative what?
Hold on. The R is in the negative direction. So it'd be,
That is true.
I was just gonna say J hat, positive J hat direction.
So up.
Yeah.
The force is definitely up. R is in the negative I hat direction. So from a direction point of view, R cross, this R1 plus cross F1 would be the negative I hat direction cross the positive J hat direction.
So are you talking about where our thumb points?
Yes,
Oh, into the board.
which is based upon this,
okay, yeah.
Oh, K hat.
into the board.
Into the board is a dot.
No,
No, is it
dots
like-
coming
Oh,
out.
no, it's,
They
yeah,
are coming out.
because the fletchings, okay, yeah. So into the board, you got the fletching showing, so it's X, so cross.
Yeah, but I have a dot there, so K is defined as out of the board.
So
So-
it's negative K.
Yes, negative K hat. So that's in the negative K hat direction. What about R2 cross, oops. R2 cross F2, what is the direction of that cross product?
This is the same.
Yeah. They're both in the same direction. There's no way they can cancel each other out. Therefore, it is not in rotational equilibrium because the sum of the torques is not 0. So we got some parallels there. Linear equilibrium. We had the 3 conditions that the total force is equal to 0. The change in velocity is equal to 0. Or the acceleration is equal to 0. If one of those is true, the other two have to be true. In rotational equilibrium, the total torque is equal to 0. We'll get to the units in a moment. The change in angular velocity is equal to 0. Or the angular acceleration is equal to 0. If one of those is true, the other two are true. Questions to hear before we talk about units? All right. Flashback. I've got doesn't matter what the mass of the box is. I'm applying a 10 Newton force over a distance of 5 meters. What is the work that that 10 Newton force is going to do to the box?
What is the work?
What is the work?
50 joules.
Yes. We just multiply them up. That's now the force that's in the direction. This is F dot delta X. So it ends up being 50 Newton meters, or as was said, 50 joules. Part of the energy chapter. I now take a lever here, 5 meters long. I apply a 10 Newton force. What is the magnitude of my torque? Assume that the force is perpendicular to the door. What is the magnitude of my torque?
50 joules.
No. How'd you get 50?
Also, would it be half of the?
I just did 10 times 5 again.
Yeah, and I just sorry, puberty. I just erased the formula, but the magnitude of torque is basically the magnitude of the moment arm times the magnitude of the force times the sine of the angle between them. If I put my two forces, if I took my force and my moment arm and put them tail to tail, I have 10 newtons going up. I have 5 meters going to the right, 90-degree angle between them. What is the sine of 90 degrees? So therefore, my torque is just R times F. So it would be just 10 newtons times 5 meters. So the magnitude of my torque is 50 what? It is not joules. That was the mistake. You're making it far harder than it is. Think about what you multiply together to get 50
Newton meters.
Newton meters. And this is one of those really lovely things about units here. A Newton meter is a joule when you're talking about work and energy. A Newton meter is not a joule when you're talking about rotation, when you're talking about torque. It doesn't have a one-word name, it's a Newton meter. Yeah, I mean, at least in the US customary units, I'll see foot-pounds of torque and foot-pounds of work. And they don't take foot-pounds and call it something else. I guess you could do horsepower, but no, that's more power. But it's one of those just absolutely lovely things. A Newton meter is not always a joule. It's a joule when you're, again, given context. So you definitely not say 50 joules of torque. When you're doing the compound units like this, as I mentioned before, but I'll say it again, please put a dot in between it. Even though capital N is not a prefix, if you did it the other way, if you did a meter Newton, which would still be correct, just traditionally it's Newton meter. If you did meter Newton, that's a meter Newton. That's a millinewton. That's a unit of force. That's a unit of torque or energy or work, depending on the contact. All right, questions up to here. I'm about to erase. All right, let's just go through one example using this idea of rotational equilibrium. And then we'll take a small break. and then we'll do something potentially completely different. I have a beam here, being held up by 2 wires. We'll make this 10 meters long. We'll say this is 1.5 meters and 2.1 meters. The beam, uniform distribution. And all that is saying is that the center of mass is the physical center of it. Mass, let's make it 19 kilograms. What I want to know is what's the tension in each wire. Before we bring in the torque, before we bring this idea of rotational equilibrium, you would need one other piece of information. However, we don't need the extra piece of information anymore.
Okay, so that's masses, okay.
Right, so. Force diagram. What are the forces acting on it?
Gravity, force of gravity,
Acting,
downwards.
and so that's smack dab in the middle. So we'll call it the weight. We can calculate it, that's just mg, which is 19 kilograms times. Oh, let's put this on a mysterious planet, where g happens to be 10 meters per second squared. So I got 190 newtons. All right, so the weight's 190 newtons. What other forces do we have?
Tension.
The rope will, the rope,
Okay, there's 2 ropes.
Both of them.
Okay, acting which way?
Well,
Up on the.
yeah.
yeah.
On which way on the beam?
Up.
I hope so. If you're not sure of that, imagine if you cut that, what's going to happen? Well, I assume it would fall, because acceleration of gravity is not 0. So I have this tension here. I'm going to call this tension 1, and over here I call this tension 2. If you don't like 1 and 2, I hope you're right. This thing is in equilibrium, linear and rotational equilibrium. And let's say that the initial velocity is 0 meters per second, and initial angular velocity 0 radians per second. In other words, just a beam sitting there. From our point of view, it's not moving. From its point of view, we're not moving. All right, let's plug in. Well, we're going through the process. So first, force diagram. Direction of acceleration is, why'd you shake your head, Olivia? Right, it's in equilibrium. It's not moving. It does not automatically mean that the acceleration is 0. It isn't moving because I wrote this up here. But if I can take that out, and that doesn't change anything else that we're going to do. All right, so acceleration is 0. So if I plug in F equals ma, facades. Coordinate axis, what do you want to make the positive direction? Decomposition. Do we need to break anything up?
Everything's on.
Yep. Right. Everything's vertical. We're good there. We would have had to break something up if we had just wanted to, just for the fun of it, make that the positive direction. But then it becomes a 2-dimensional problem. Equations of motion. Now we're doing the equations of motion. What will be the equation of motion?
ft1 plus ft2 minus, wait,
So far, so good.
equals 0.
Yeah, there we go. ft1 plus ft2 minus the weight is equal to 0. Yeah, we just sort of point out here, it's called the equations of motion. Even though it's not moving, it's still called the equations of motion. Equations of motion are not the chapter 2 equations, or chapter 3. So chapter F equals ma is the equation, the basis for the equation of motion. And equations have to have an equal sign or an inequality sign. Although if you just do that, that's an expression. That's not an equation. Equations, for the most part, need equal signs. Just a little tip for those who are doing test corrections. All right, I know what the weight is. That's equal to, next step would be substitution. So I have ft1 plus ft2 minus mg equals 0. Or we could just take mg over to the other side. I know this is 190 newtons. We figured that out already. But I have one equation and two unknowns. It cannot be solved with just F equals ma alone. So now we bring torque into it. So when you're dealing with rotation, F equals ma is the basis for the linear stuff. For the rotational stuff, tau is equal to I alpha.